Well, hello guys, welcome back. And what we're into now is the next section in lesson 1, which was a bit of code and a bit of description on various ways to start up applications on your Amiga and how you support this with the code you're doing. As you, if you've experienced with dealing with this on other platforms and the standards with C, that the normal way to do it is using the argc and the argv. Obviously on the Amiga, you've got a couple different ways to start applications. One of them is by using the shell, the simple old way. You type your program name, and you fire it up. The other way to do it is obviously by double-clicking on the program or double-clicking on a project icon that uses your program. And obviously those are the GUI ways of starting an application on Amiga OS. Amiga OS supports this standard method of starting an application where your main function is called and it uses the argc and the argv variables. That's standard C code. And basically argc is an integer that tells you you've got a certain number of arguments. The first argument is always going to be the name of your program. And then you get also pointers to strings that are each one of the additional arguments that your program gets. So you have a way of saying your program just got a command to copy a file from A to B. Those are your two arguments. Your second and third arguments. Your first argument is the name of your program. That's standard C code. Amiga OS has provided you more advanced ways of dealing with both starting from the CLI and starting from the workbench and all of the various ways that the workbench can run your application. In the materials that you guys are going to get from this lesson, you're going to get obviously this wiki page. It ends with source code to the example that shows you how all this works. And we're going to distribute that to you all before this seminar is all over. That initial method of doing it, like I said, they just deal with these simple variables. There's no checking for anything in terms of whether or not the variables are what your application was looking for, the parameters, and so on. Amiga OS came up with, here's an example of the source code for how the ISO does it. You've got a, basically you could have a for loop that basically goes through and says, how many arguments have you got? Print out each one of those arguments. Like I said, there's no checking for what it does. It's pretty basic. It's up to you as the person writing the program to test what you got, figure out if it's what you wanted, tell the user they got something wrong, all of that.
I added the get opt thing.
You added the what?
Get opt.
Oh, get opt. Let's see here. So, yes, well, so as Stephen's saying, there are ways to add to it. But since we're all programming for the Amiga, we won't bother with those things. We're using Amiga OS.
There's other libraries to parse those, yes.
Yes. The Amiga method of doing it is it comes off as slightly more complicated, but it provides a lot more power. And what it is you have a function called readArt that is this syntax right here. And what it does is it actually takes the input that your application gets and parses it against a template. On any of your computers right now, you can open up a shell window and type in any one of the Amiga OS commands, like dir. Type in dir space question mark. You're going to get what's called the template for that command. It tells you what functions and commands and parameters that it'll take. That's an example of this function right here. That you've got the ability to say, you can define a template using any one of these keywords and what things it'll take. You can have a switch, for example. So, for example, the best example of a switch I can think of is reboot with fast. Fast is a switch that says, reboot your Amiga quickly. Don't cold boot it, warm boot it. Don't do that now. So, those are examples of the templates that you can define. These templates, and for example, here's an example of a template where you're saying, okay, I am going to have a keyword that is test. I want to receive number and get a number back from the user and a file name. You could set that template up, and that's how your input is going to get parsed. if the user goes in there and types in the name of your program, question mark, he'll be told this is what this program prefers, is looking for. When he types his name of your program and the parameters, it's checked against that template, and the results that your program gets, this, like I said, is this template right here, provides for these variables. That's what you're going to get from your user. So you have the ability to say, this is what I'm looking for, and the operating system will test what the user gave, and if it doesn't work, then your program won't have to worry about it. It'll get kicked out. So when it gets the results, what you do is, before you call readargs, you set up an array of pointers that'll get filled in with parameters come back from the readargs function. So you call readargs. What ends up happening is that it parses out what happens. The first item in this example is test. The second item is a number. The third item is a file. Readargs will parse it out. If it gets test, that first item will tell you that the test function was called up. If somebody gives you a number, the second item will be the number. It doesn't matter how they do it. If the user puts it in there, your program gets it. You didn't have to parse it out and figure out what they did, whether or not they gave you the variables you were looking for.
Small typo.
What's that?
Text keyword should test.
Ah, yes. Text.
I just noticed.
Yes, I know.
We'll fix it.
That's my typo.
So all the error handling is being done.
By the readargs function. What happens is it gets the parameters that come in when your program started, and it parses it all out. It does all that. If it doesn't work, it kicks back out again. If it does work, your application gets the results in this array that you've filled with zeros here. When your program's called, it comes back and it is able to say, well, was the array number 0? If this was not null, then you know that text. The typos here again.
Yep.
Test flag was called. And in that way, you don't have to go through and figure out the order in which the things, who knows what order the user types their stuff in. And if you are coding it yourself using the Unix method, you've got to go through and parse all that out. What if they put the number first and then test and then the file name? Well, you've got to go and figure that out. What order did they put it in? readargs does that all for you on the basis of the template that you were given. So, and after it's all done, so you're getting all the information back, and you can test the arg array for what happened and whether or not it was right or not, and what the value was. When it's finally all done, then the memory that was allocated by readargs, you got a free, give the memory back, you can keep on going with your program. You've got validated data that came in. So that's a simple example of the Amiga way of doing it, of starting a program from the shelf. You're going to write a CLI program that's going. But clearly, you're on an Amiga, and we also do things with a GUI. Any program is going to typically can run from a GUI or from a shell. With Amiga OS, you have the ability of checking to see, was your program started from the workbench or from the CLI? And the way that's handled is that the argc value, all of this is based on those same standard things, argc and argv. If the argc value is set to 0, then you know the application was started from the workbench. And your application can then deal with that, with finding out what application, what parameters and things like that got sent to your application. Now, bear in mind, and I talk about it here, there are several different ways your application obviously can be started from the workbench. One, you could go to the icon of your application, double click it, your application was started. Two, you can go and say, let's say your program is an image viewer. Well, you could go to a JPEG image and say, the tool for my JPEG image is my program, and double click that JPEG. Your program starts with that file name, right? So your viewer now is going to view that file that was double clicked. The third way is you can actually select your program, shift click and select and double click the JPEG image, and the two of them are started together. So there are three different ways the workbench allows you to start an application with files or not. The way this works is that you get a pointer that in the argv variable, you get pointers to the WB startup structure. And what that does is it gives you information on the files that you were passed in your application startup. That structure, as you see here, is going to be, if argc is 0, then you have that structure, then you can declare and get the variables. And there are all the contents that you get out of the variables. Out of these, you really want to know how many arguments were called, and then also the argument list that tells you the information on the things that were passed. Just like with the argument argv variables, when you're started by the shell, you always have the first argument is the path to your program. So if your program wants to run and it needs to know where it's located, that provides you with a method to find it. And then all the successive arg list functions tell you where all the files are, what files were given with your program. Now, one of the things that happens with these arg lists is that you have essentially pointers that tell you, one, you have a lock descriptor, and two, you have the name of the file that came with that. And essentially, if you want to find out where that file is, you go and examine the lock. You don't have to sit there and allocate file memory for that. You just find out where that file is, and then you have the ability to read both the file location and path, but then you also can get the information from that file in terms of this example code right here would give you an example of how to print out that information. And in the source code that you've got in this example, you'll see how this goes. Now, when you get this, you have the ability to go and put tool types in any program, both in the workbench icon as well as in the files. You can go into the tool types and you can set up the variables. This essentially the same way like you set up a shell command. You typed in there your name of your program and you said test, and you said the number is 23. You can set these tool types in your program, and you can also do it in the file. And essentially what happens is that you use the lock descriptor that is a pointer that is given from the operating system to the file that you're calling. And that essentially, you have the ability to go and say what tool types were given, and it provides you with a tool types array. You put links in here, didn't you? But you have the ability to call the tool types array here. Except now the question is, does it work?
It'll work eventually. It's a little slow, the internet connection.
It is. Maybe I shouldn't have done that.
There it is.
So, and this is actually an example of how the wiki works. The wiki is tied into the RKM that Stephen has put online. And that, obviously, we have the ability to go and put links in where you can click on a link and get to the documentation. And as this stuff all gets updated, you're going to see this information get updated to suit OS4 instead of what might be, in some cases, old code. The tool types array, this is the original documentation on the tool types array that explains what information is stored in there. And essentially is telling you all the basics about what is in the array and what variables are set there. And essentially what you do is with each directory, you go and get the tool types array, and you've got the directory information by calling the current directory on that. On each file, the first one is the application, then any of the successive files are going to be the successive pointers in the arg list right there. And essentially what happens is you have to lock it, you get the directory information, and then you can check the tool types to see if your tools are set. The way it works is that Amiga OS then provides, actually, oops. doing? So each directory then allows you to find the information on the file. Now, to keep somebody from moving a file while you're looking at it, those files have, the directory gets locked where that file is. So what happens is you move to that directory by doing the current directory. You get the information on the file, then you move back to the previous directory by calling current directory with your old directory again. The information that you have right there is the get disk object new. This function then gets the tool type information, and either it tries to open up the disk object, basically the representation of all that information on that directory. And then once you've got that, that can either be the info file, or in the case where you have applications that don't have an information, an icon file, an info file, this function will go get the default icon for it. So you guys all know we have def icons, and they're all the def JPEG file or the def text file or whatever that's all sitting in your system. So we have this function, get this disk object new, that is smart enough to go on off and get either the information from the icon or from the default. Get the information from that icon, and your application again then can examine that. Keeping the parallel path of parameters and the shell, like I said, you have the tool types. The way that works is you get the disk object. If the disk object opened, there's all the information that's in that structure. Now the critical thing is the tool types. And the way you access that is you check the tool types to see whether or not the tool type you want is there. Was the test variable set? Was a number set? If that number was set, then what happens is you use the find tool type function, and you basically say, was the tool type set for test? Was that tool type there? If it's there, you got it, your program knows that. And you basically are able to say yes, true or false, it's there. And in that way, you can run this on every single disk object your program gets. So it can either check your program to see what tool types are set, or you can check every file that's sent to the program. So if you want to, you can, on a file-by-file basis, pass parameters to your program, or you can have parameters in the program itself. Everybody with me?
So maybe,
Behind you.
so maybe I missed it, but let's say test equals 2.
And what happens is, you're going off and you get the test, and then the argument that gets passed back by the find tool type is the setting for that. If not, it's not.
So if TTR is true, there's a Boolean that gets set.
If
that says I
TTR is
found
not null,
it. Is not null.
is not, yes.
Then I at least found it.
And TTR is the value.
And it is the, but if
Yes.
the value is just a keyword,
Then it's going to be true or false. Right?
then it's just Boolean. But if it is an actual value coming in, like a path or a number or
There's
something like
set in
that,
there, right.
then it's the actual the result.
Right.
Well, in tool type land, everything's a string.
Everything is a string. So if
Yeah.
you do type conversion to move between,
Yeah, you actually have to convert the string back into a number.
is that also true for the CLI when you enter
No,
in data?
then in that case, it's actually a number.
Okay.
But what it is, you know, you've got the ability to find all the different ways that you can pass parameters to your application. And obviously in the workbench, you have a number of different ways, because there are different ways to start your application. Either by running the program, did that program have things set in its icon? Or running a project, a JPEG file. Well, you could save in the JPEG file things like scale 50% and rotate 90 degrees. That could all be set in the tool types. Your application as a viewer could say, oh, look, I was just passed a JPEG file. Did it have any instructions on how to view it? And check the tool types for scale equals 50%, rotation equals 90 degrees or 180 degrees. And in those ways, your program can say, oh, look, I was passed this file. Oh, there's a setting for scale set. Let's do that. There's a setting set for rotation. Let's do that. And you essentially check these different settings, and then you can find that, and there's the sample program that is at the end of this, and you guys will get it, gives you all of these pieces of code in actually a program that you can run, that either you can use it from the shell, or you can use it from the workbench, it's in there. And
And you said that also holds true for things like the default icon.
and it holds true for the default icon. So let's say you want every single JPEG file to always be scaled 50%. Well, you could go into your environment archives to where all your def icons are stored and set the def icon for def JPEG to scale equals 50%. And if your program, obviously this is now extrapolating our example probably uselessly, but your program would say, oh, okay, look, every time a JPEG is double-clicked, scale it down 50%. And in that way, it passes the parameter to your program. And finally, then it gets a little bit trickier when you want to get actually the path and the file name. Now, up to this point, we've never really been dealing with the full path name to your program, to your files. You always get a directory lock. You get a disk object to the file that basically is just a pointer that says, okay, here's a place in space, your file system with a file there. And then you examine that pointer, that place in space, to get its tool types and then to check the tool types and all that kind of stuff. If you actually want to get the file name from it, then it gets a little bit trickier because you don't know how long the file name is going to be. Your program could have just simply a file on the root with sys and get simply a file name that's sys : testimage.jpg, and it's handled in a few dozen characters. Or it could be buried 10 directories deep where every single file directory name is 20 characters and the file itself is 100 characters long. And now you've got to have a 4,000 character long string for getting your file name. Because we always just dealt with a pointer to that file, we never have to worry about that. If you actually want to get the file name, what you have to do is you lock the directory and you use this function, name from lock. And you basically lock the directory where the file is. As long as it worked, you get the name from lock. But you have to give it a certain length for the number of characters. Everybody I was able to talk to said, try 2,048 characters. It's a reasonable guess. But if you have the example of 10 directories deep with every directory with a 50 character long name, it's not going to work. This is going to fail. It's not going to work. You're not going to be able to get the
Name from lock will tell you it's not big enough.
It's not big enough, right. This is going to fail and you won't be able to do the print of the file name. Either you could simply have your program gracefully disappear. Bad thing to do. Really what you got to do is you got to go and tell your user that the file name, 2,048 characters, actually it's not file, it's path and file name, is longer than that. And tell them, look, the file name's too long. We're sorry, we can't handle this, and then quit.
Does that include all the backslashes and colon and all that?
It's the full path, yeah.
Okay.
That would be the basic, minimal way of doing it. Tell the user at least what went wrong. If you really want to be a masochist and you want to make sure your program works from here forever, go back. If that fails, go back and allocate more characters. Put this in a loop and keep going around until you finally get the name in a big enough string of characters. But
If I could just interrupt for a brief moment. Why this is exactly why a lock was given to you, right? Because a lock is like 4 bytes.
yeah.
So you don't have to know what the string is to get
Yeah,
it.
exactly.
And
So you always
use,
get this pointer to the disk
There's a
object.
pointer to the object. And
Yeah.
you can use the DOS library function open from lock and never look at the file name.
Right.
You don't need the file. File name's only for users, really.
Okay.
Right?
Yeah.
As far as your code goes, you can avoid it. But when there's an error, they kind of want to know which file. So I just wanted to mention that.
Okay.
That's why we use locks, because they're so small and compact.
Right.
Easy to deal with when you're encoding, but users
Right.
don't like locks. It's a bunch of hex digits.
Yeah. So, and this being C code, you're always dealing with pointers, and just a pointer to a chunk of memory, or a pointer to in AmiWest, a structure that represents an object on the file, on the disk object. So that's why the last thing in this whole tutorial was to tell you about the nasty little secret of how to get a file name and how to deal with it when it's longer than a certain guess. Obviously, you don't want to go through and like make all your file names, if for some reason, like you're printing out a list of files for your users, all your file names 10,000 characters long, if in reality they're all going to be about 50 characters long. You're just wasting your time and memory. Would be the Windows way to do it, but but in this case, the idea is pick something reasonable and then deal with the odd circumstance if it fails. And which was the last thing that we were saying here, that you've got to basically deal with the error trapping. The other thing which you get, what you're getting from name from lock is, you're getting the path name. So you actually have to combine that with the actual file name, which is what you get before. So you have the ability to use a function add from part that actually deals with the file name and then deals with what you get back from the name from lock. So what you're getting here, name from lock gives you the full path name. And you add to that the add part.
Right. So yeah, that's true. So you go current there and then open it.
Yes. So what you're doing is you get the path name and you get the file name. You're going to put them together. And obviously in some cases there might be a colon there, or it might be, if it's on the root of a drive, path name might just be system : what if it's system / pref / envar arc / and then putting those all together, if you're programming it, you got to sit there and go, oh, well, do I add a / or not? Or does it end with a colon? If you just use add part, it puts all the pieces together for you and handles that. And once you're done, the result of that, you can print that out, the file name that you get from that function. Again, is it long enough? If it works, then great. If not, that's why that if is there. If it doesn't work, you're going to get a 0 and you knew your file name was too long. As again, we need error trapping here to check that the combined file and path name is big enough. So what we give you is a source code. I know you guys really want to see all this. There's all that nice source code there with nice comments and everything.
It's pretty.
And it's color-coded in Steve's wiki. So in that source code, this is a little application that should have put the program on here.
Well, I was going to ask these guys actually. Did everybody cut and paste this program, or did you try it at all? Nobody? No?
Okay. What we need to do is we'll give you guys the source code. Essentially what it is it's a program that goes through all of these code samples that you've seen in this text right here came out of that sort of program. So we're going to give this to you because, we're trying to make this, we start off with it from a portable standpoint. The C standard is that you have argc and argv. Argc is the count of variables. Argv is those variables when you start from the shell using the Unix method. So you use that method to get it. The first thing you do is you check to see if argc, if you start it from the shell, will always be 1, because you always have the name of your program. If your program started from the workbench, it'll be 0. So your application, and this application does that, will check whether or not it's 0 and it was started from the workbench, and then it'll go through all of the stuff we talked about with the workbench. Or it'll check if it's 1 or higher, and it knows that it started from the shell, and it calls the read args function to parse it out from the shell. So this program that you guys are going to get basically can be run either from the workbench or from the shell. And when you run it from the workbench, you can either double-click just it, set somebody else to use it as a tool, or shift-click 2 things, and it'll parse that all out and look for tool types and print out what tool types it sees.